Hello everyone, my name is Yang Zhang from IBM Research. Today I will introduce our paper, Speech Self-Supervised Learning Using Diffusion Model Synthetic Data, a collaboration work with UIUC and UCSB. Let me start by quickly going over some background about speech self-supervised learning, or speech SSL. Speech SSL, just like SSL in other domains, assumes that we have a large unannotated dataset. And so we can use this dataset to pre-train a speech representation network. The pre-training task is often similar to the next token prediction or mass token prediction task, as in pre-training a language model. The resulting pre-trained network is then fine-tuned on a small annotated dataset to perform certain downstream tasks. The key to successful speech self-supervised learning is that the unannotated corpus should be sufficiently large. In most cases, the pre-training data should be at least 1,000 hours. However, for many languages, collecting such a large dataset is not as easy as it seems. Here, I'm borrowing a graph of a recent research effort in collecting speech data for over 1,000 languages. The horizontal axis represents the languages, and the vertical axis the number of hours collected for each language. As can be observed, for almost all the languages in the world, the numbers of hours is below 1K, meaning that collecting a large unannotated dataset is challenging in many scenarios. In situations where the pre-training dataset is limited, it becomes crucial to maximize the amount of information captured from the pre-training dataset. Therefore, we raise the following research questions. Do the existing SSL techniques fully extract the information in the limited pre-training dataset? Could we further extract information that is overlooked by the existing SSL approaches? In this paper, we propose DiffS4L, a speech self-supervised learning method that augments the limited pre-training dataset using a diffusion model, which can contribute to a much better pre-trained model, particularly under low-resource scenarios. More specifically, assume that we only have a small unannotated corpus, say less than 100 hours. DiffS4L essentially augments the dataset using synthetic data, which is then used to perform the pre-training using the standard pre-training methods. The augmentation process consists of 3 steps. As the first step, we use a small unannotated corpus to pre-train an initial speech representation network using the standard speech SSL methods, such as Wave2Vec or Hilbert. Note that this initial representation network is of poor quality because of the limited dataset size, but it is sufficient for our augmentation purpose. Once the initial speech representation network is trained, for each speech utterance from the small dataset, we can obtain its initial speech representation. As the second step, we feed the initial speech representation, together with a speaker embedding extracted from the original speech, to a conditional diffusion model, which is trained to reconstruct the original speech. The diffusion model is trained only on the original small unannotated corpus. After the diffusion model is trained, we can then use the diffusion model to generate synthetic speech. However, instead of directly feeding a speech representation and speaker embedding as is, we first modify them before they are sent to the diffusion model. In this way, we can generate a good variety of synthetic speech that is different from the original real speech. Therefore, the only remaining question is how we modify the speech representations. Note that speech contains rich information across many levels, including content, speaker, and prosody. So the modified speech should also contain enough variations in all these aspects. Therefore, we designed the following 4 levels of variations. The first level is the original speech itself. Here is an example.
And sharing her house, which was nearby.
The second level is the diffusion model reconstructed speech using the exact original speech representation and speaker embedding. The reconstructed speech is almost the same as the original speech. However, since the initial speech representation does not fully control the prosody, the synthetic speech will slightly differ from the original speech in terms of prosody. Here is an example. Please pay attention to the prosody of the word which.
And sharing her house, which was nearby.
Now, which becomes a rising tone instead of the dropping tone in the original speech. In the third level, we change the speaker embedding that is fed to the diffusion model. So the synthetic speech contains the same content, but in a different speaker's voice.
And sharing her house, which was nearby.
Finally, in the fourth level, in addition to changing the speaker embedding, we also partially mask the speech representation. The synthetic speech would then contain novel content fabricated by the diffusion model itself.
And the ICML nigh.
As you can hear, the speech contains almost nonsensical babbles, which implies that the diffusion model cannot learn the syntax and word structure in speech. However, we will show that even this nonsensical babble can help the pretraining. To test the performance of DiffS4L, we use the LibreSpeech 960 as the pretraining dataset, which contains 960 hours of unannotated speech in English. We consider two pretraining settings. In the low resource setting, we sample only 100 hours of real speech, then augment it into 960 hours by synthesizing 430 hours of same speaker and novel speaker speech, which are level 2 and level 3, and 430 hours of novel content, which is level 4. In the high resource setting, we use all of the 960 hours of real speech and then augment it into 2,400 hours. We use two standard pretraining techniques, Wave2Vec2 and Hubert, to train the initial and the formal speech representation networks. We compare four augmentation techniques: no augmentation, Wave2Vec-Aug, Wave-LM, and our proposed DiffS4L. We evaluate the performance on several downstream tasks. The first task is the English ASR, where there are 10 hours of labeled data for fine-tuning. The results show that DiffS4L can significantly reduce the error rates for both pretraining methods. We can achieve even larger error reduction when DiffS4L is combined with Wave-LM. Notably, the results in these two boxes are both pretrained on 960 hours of speech. The difference is that the results in red are on 960 hours of augmented speech, whereas the result in blue are on 960 hours of real speech. We can see that the gap is already very small. To test other downstream tasks, we use a superb benchmark, which includes 8 different tasks other than ASR. The results also show that DiffS4L can achieve the best performance in almost all tasks, both in the low resource setting and the high resource setting. Next, we test the performance of ASR for 13 more languages, and the results consistently show the benefit of DiffS4L. One final experiment I would like to show today is to investigate whether the 4 levels of synthetic speech are all helpful, particularly the level 4 nonsensical babbles. What we do is that we take the low resource setting, keep the original speech unchanged, and keep the total speech to 960 hours. But then we vary the proportion between the level 2 plus 3 and the level 4 babble speech. This graph shows the English ASR error rates under different proportions, where the leftmost point corresponds to no level 2 or 3, and the rightmost point corresponds to no level 4 babbles. The results show that the best performance is achieved in the middle, where all 4 levels of speech are included. This implies that level 2, 3, and 4 variations are all helpful for the downstream performance. To sum up our findings, we find that diffusion model is able to capture the information in speech complementary to what SSL learns, and therefore DiffS4L can significantly improve the SSL performance in various downstream tasks and languages. In addition, we find that synthetic speech with different levels of variations are all conducive to SSL, even the seemingly nonsensical babble. With that, I will close the talk today. Thank you for your attention.